Hi, everyone. We are delighted to have Ryan Rogers today. He's a staff software engineering and data science applied research at LinkedIn. Before that, he was a senior research engineer at ML privacy team at Apple. Ryan received his PhD from UPenn with Michael Currens and Aaron Roth as his advisors. Since then, his research has mainly focused on differential privacy and adaptive data analysis in numerous applications. Today, he will talk about privatizing one-shot and continual observation histograms with applications. So without further ado, I invite Ryan to start his talk. Thank you.
Great, thanks for having me. Yeah, so this is kind of a joint collaboration across several different people at LinkedIn, and we're kind of spread across different orgs and different teams. So it's been kind of a great project to work on at LinkedIn. Great, so I'll get started with first a brief introduction. I'm in the data science applied research team. It's made up of 3 different tracks. One is in experimentation and causal inference. Another one is in forecasting and anomaly detection with root cause analysis. That team just recently put out some open source on some forecasting tools called GrayKite. And then there's also where we work on various technologies, including differential privacy. And we are hiring, so please reach out to me if you're interested. So let's get started with sort of the overview of what I want to talk about. One is that I'll give a sort of overview of what differential privacy at LinkedIn sort of entailed and takeaways there. And then I'll talk about some differentially private top K algorithms with some applications to them, and then sort of end off with applications or more sort of the model for streaming and how that can be later. Okay, so let's get started. So our team's mission is that we want to be able to maintain the usefulness of data while still protecting privacy of members. And here's a sort of schematic of sort of how data is sort of created and then used. It's not very specific to LinkedIn, where we have users that generate content, and then we have data centers that are collecting this data, and then we want to build applications on top of this data, like informative dashboards, data APIs, or machine learning models. And depending on sort of where you want to put trust in the system, you can incorporate different models of privacy. Only 2 of them here, but there's great work on sort of hybrid models that sort of combine the 2. So in the local, sort of privatized data before it's even collected. And lots of great deployments of this, including at Microsoft, Google, and Apple. Microsoft in collecting telemetry data, Google in collecting malicious homepages on the Chrome browser, and Apple trying to find the most popular emojis or new words that people are typing on iOS keyboard. In the global model, there's also been some recent applications of that, including the 2020 census. Microsoft and Harvard's IQSS has joined forces to bring out this open data DP project, as well as several open source projects, including Google's open source. And so it'll be this sort of global that we'll be focusing on here at LinkedIn, where data is already collected, and we want to privatize things before they're shown to perhaps people external to LinkedIn or to specific teams. So after meeting with lots of different teams at sort of where differential privacy could be included, there are several key takeaways that we had when we met with them. One was that there's a lot of existing infrastructure for computing aggregates very quickly on distributed data. So we don't want to just complete this existing infrastructure. We want to sort of build algorithms that can utilize these systems so that we can get the scalable solutions that these systems already provide. We want privacy to be tunable, which is why differential privacy is so appealing, but we also want to make other constraints are sort of tunable as well. We don't want to just turn on a differential privacy light switch and then everything just runs 10 times slower and there's no way to fix that. So we want to sort of also be able to tune runtime. And also meeting with lots of different teams, sort of the main task that we needed to do was we needed to privatize counts or count vectors or histograms, is what I'll refer to them in this talk. So if we can build algorithms that can be used on top of the existing infrastructure that can privatize histograms, that could knock down several applications and be able to privatize lots of things at once. So let me sort of give a rough idea of existing systems. Imagine we have some sort of highly distributed data set, and there's some that can already compute these aggregates on this highly distributed data. And the output of this is going to be like this already aggregated version of the data. So we can sort of ask the black box, hey, give me top K of some queries, and it will provide sort of a limited number of results. And so it's this histogram that we want to be algorithms to. And so what this prevents us from doing is being able to like go to the raw data records and try to like sort of enforce some sort of sensitivity constraint on there, sort of limit the number of records that one user might be able to include in the system. So rather we want to sort of just take this histogram and just apply differential privacy on top of this. And for all the use cases, we're partnering with Pinot, which is this open source project that's sort of this top K prime solver that is sort of the analytics platform of choice at LinkedIn. It powers several use cases like who viewed my profile. Okay, so that's kind of a rough overview of what differential privacy, sort of initial conversations of differential privacy at LinkedIn, and sort of to give you the main problem there. So now let's talk about, well, how can we privatize top K queries? So the SQL query of interest here will where we just want to know what are the counts of users with certain skills in each country. So we're going to do a group by country. And so this is essentially just going to provide a histogram over all countries. And we want to have sort of the counts on each country. And these are like the number of people that have each skill, that have a particular skill. So now when we run the thought experiment in differential privacy, we ask, well, what happens if we remove a user from this histogram? What can happen? Well, maybe we know ahead of time that like a user can only be in at most one country. So a user may or may not have that skill. So might drop this count in exactly like one place. And so it's easy to privatize this histogram. We can apply the classical Laplace mechanism or a Gaussian mechanism to add noise to these counts. And then the result will be some noisy histogram. And we don't even have to limit the number of things we release. We can just report this entire histogram back to the user. So let's just sort of have exactly a very similar SQL query, but slightly change some of the ways that we're doing a group by. So we want to ask a query like count the number of users in the US that have each skill. So for this, we're going to have a histogram represented over all these different skills. And now we run the same thought experiment in differential privacy. Well, how much can one user impact this histogram? Remove this person from the data set. One user can have lots of different skills. So potentially all of these counts can drop. So we call this a high sensitivity query. And let me just point out here that I think some terminology might be a little confusing. So I think a lot of times we refer to histograms in differential privacy as somebody just being able to affect one or two bins in a histogram. Like these SQL queries are like almost identical. So I'm going to be talking about sort of low and high sensitivity histograms where somebody can modify lots of counts. So one thing that we can do here is we can just sort of limit the number of things that are actually shown back to the user. So rather than sort of having this query that is trying to group over all skills, let's sort of add this component to the SQL query that's going to only release the top 10 results from this. I just got a note that said the internet is unstable, but hopefully you all can still hear me. So if we instead try to run the query, like what are the top 10 skills in the US, then what we can do is we can sort of have privacy that will only depend on the number of things that are returned. So we can do that by implementing the exponential mechanism from McSherry and Talwar in 2007 is we're going to sample each element with some probability that's proportional to the exponent of like the count. So we're going to be selecting things that the larger the counts are, the higher chance we'll be selecting those elements. And so to implement the exponential mechanism for top K, you just select the top one, remove that from your domain, then select the second highest and the third, fourth, and fifth, all the way up to 10. And so now your privacy is only going to be the number of things that you asked for, so K things, despite somebody being able to affect lots of different bins. So we're going to be releasing K of these, and we can ensure K epsilon differential privacy, or we can apply sort of advanced composition here. Okay, so note that if you are worried about sort of the L infinity sensitivity of these queries, so one person being able to modify lots of counts in a single bin, we can change the count to like a count distinct over user ID. This will ensure that the L infinity sensitivity is 1 rather than sort of unbounded if you don't know anything about the count. So now if somebody were to be able to modify all the bins and we do a count distinct, we can just limit the amount of privacy that's consumed by just releasing just a few counts, like a top 10. But put these two algorithms, distinguish them, I'll call the L0 restricted sensitivity setting. If we want to privatize that, we don't need to actually have a limit clause in the SQL query. We can just release the entire histogram, but we can just apply the Laplace mechanism. Whereas in the L0 unrestricted sensitivity setting, we have the classical exponential mechanism to release sort of a limited number of queries. Okay, so just a quick aside that if we want to be able to implement the exponential mechanism, so there's like a folklore result that says that if we can actually do exponential mechanism by doing report noisy max, but with Gumbel noise. So we add Gumbel noise to all the counts and we select the one, the arg noisy max from this. And this is precisely the exponential mechanism. And it turns out in a result that David Derby and I had is that we can just simulate a repeated exponential mechanism in one shot. So this algorithm of like sort of peeling the exponential mechanism like K times to get a top K. Rather than that, you can just add Gumbel noise to all the counts and take the top K of those in one shot. And it turns out that this is equivalent in distribution to just repeatedly sampling exponential mechanisms. And so you can get advanced composition with this one-shot approach. And so for more information, there's a blog post that we have on differentialprivacy.org on this. Okay, so here are the two algorithms that we have. I'm just going to rename them just to sort of point out that one is going to be adding Laplace noise and maybe reporting the top K noisy counts, but privacy is only going to depend person can modify, versus the known gumball algorithm where somebody can modify lots of different things, but we're going to only pay for the number of things that are returned. Okay, so in doing this, one thing to point out is that the algorithms will require us to sort of know the domain of these histograms in advance. So if you want to know the top K skills, you need to say in advance, here are all the skills that somebody could possibly have. And so solving top K subject to differential privacy is like one of the most fundamental problems that we want to be able to solve. And so naturally, there's been lots of work in solving top K. Several things in the local model, also referred to as the heavy hitters problem, lots of great work there. And also in the global model of differential privacy as well. But one thing to point out is that all this work sort of requires either knowing some structure on the data domain, something like maybe I want to know the top words that contain at most 10 letters. So you can sort of build this up by like finding knowing that there's 26 letters and finding sort of prefixes, popular prefixes in this, or sort of building up these words in a more efficient way. Or you need the count of every element in this entire domain, rather than sort of saying that we only have access to a top K prime. So I want to motivate what I'm going to call the unknown domain setting, where we typically think of the domain as being very, very large, or just just completely unknown. And it might be the case that existing infrastructure can only fetch top results and not return the entire histogram. It just might be way too big. Maybe we're asking for the top articles. We possibly don't have all like a domain or dictionary of all the possible articles that are being shown on LinkedIn to sort of be able to figure out what are the top. We have access to the entire histogram over all the possible articles that people have actually clicked on. We only have access to like maybe the top 1,000. And so, as I pointed out, a lot of this prior work was working with frequent item sets, where you sort of know some structure on the data domain. And so this will allow us to sort of prune the number of things we need to query. And note in the sort of restricted sensitivity setting, there's a lot of, there's some related work on sort of if you know the entire histogram from Korlova et al. And also recent work from these folks at Google. So let's think about how we could privatize this histogram if we only have access to like a top K prime when we're trying to solve for top K. So imagine that this is sort of your histogram that you want to be able to report maybe the top 5 counts, but you only have access to the top 10. So maybe this existing infrastructure is only being able to give you the counts up to category 10. And so how can I just report the top 5 from this? Well, one thing is natural to try. Why don't you add Laplace noise or Gumbel noise, and then take the sort of top 5 results from these noisy counts. That's not going to work, because if I look at a neighboring data set, one person being removed might change category 10 to falling below the red line, and category 11 might pop up now above the red line. So in this sort of neighboring data set, one person can actually create category 11 from showing up in the top 10, whereas it wouldn't have been there in the neighboring data set. And so we're talking about events that happen with probability 0 in one outcome or one neighboring data set, versus the other actually has a decent chance of showing up in the top 5. So the problem is that new elements can appear in neighboring data sets. Okay, so this attempt isn't going to work. The other attempt that we have is like to include a threshold as well. So what you're going to do is you're going to take the smallest count that you actually have access to, add a little bit more to the smallest count, something that's going to depend on the privacy parameters. And then you're going to add noise to all the counts that you have. including this threshold that you've created. And now you sort everything up until this threshold. You only report the top K things that are above the threshold. So that means that possibly you actually have fewer than 5 things that are actually above the threshold. And the way that you would set the threshold is so that new elements can appear with only small probability. But note that this can return fewer than K results. And so you want to sort of make sure that you can fetch more, if you want a higher chance of returning actual K results, is sort of change the number of things that you actually access. So maybe rather than fetching the top 10, you go and you ask for the top 25. And this is precisely like our tuning knob for runtime by incorporating differential privacy. So if we have a top K query, maybe we ask for top 10 times K or top 2 times K. That's going to have an impact on runtime, but it will also ensure that we can actually return K results more frequently, sort of this power law on our data distribution. So I heard some audio. Is there any questions so far that I? Okay, I'll pause in a minute to just stop for questions a little bit more. So let me just point out, like, sort of the algorithms that we have for private data analytics call out that the first 2 algorithms that I talked about are the sort of work in the known domain setting, where we know the histogram, we have access to all things, and we know the labels of the histogram as well. Now in the unknown domain setting, where we don't know the labels and we don't know that we're getting the entire histogram, we have 2 algorithms, one with Laplace noise and one with Gumbel noise, in these sort of 2 settings, the restricted sensitivity and unrestricted sensitivity settings. And so one thing to take away with this 2x2 grid, and this is sort of what I use to sort of talk about the algorithms that we have to privatize histograms at LinkedIn, is that if we don't know anything about the histogram in advance, we don't know what the labels are, we don't know the size of it, nor do we know how many things the user can modify. We have like a default algorithm. We have this unknown Gumbel algorithm, but this is sort of going to charge us the most in privacy. And it's also going to sort of not be able to show us a full top K because a certain number of things might be below the threshold. But if we can do more onboarding with the teams, then we can sort of push task more toward the upper left cell. So if we know the domain, now we don't need to enforce a threshold. We can use known Laplace or known Gumbel. And if we know that a user is only modifying a certain number of things, maybe this is sort of ensured as data is collected, then we can sort of move to the restricted sensitivity setting and pay a small cost. So let me stop there and see if there's any questions on these.
Hi, Ryan, I have a question. So the unknown Gumbel, that was a algorithm with or those 2 algorithms on the bottom, those were the algorithms where you set a noisy threshold.
Yes.
And use that to kind of, so you get like the top 25 or whatever, and from that try to extract the top
5, yeah.
Yeah, right, whatever it is. Okay, thanks.
Yep. Yeah, and like the algorithm, yeah, Laplace noise, and we return the top K or whatever we have above the threshold. Gumbel noise, but the one twist is that exponential mechanism, we can only return the arg noisy max. And so we want the counts too, we have to sort of add independent Laplace.
Yeah, thanks.
Yep. Okay, so let me present some applications, because these algorithms have been pretty helpful with us in privatizing several things. I'll talk about 2. So in one application that we had was applying to labor markets data. When the sort of pandemic began, we wanted to sort of see how changing. Like this was particularly interesting, like right when the shelter in place restrictions were happening and sort of everybody wasn't going to work anymore. We wanted to sort of know what jobs were actually still hiring and what were the companies that were hiring the most and what were the skills in these in-demand jobs. We wanted to provide this data to policymakers as well as individuals to sort of figure out like what skills they need to acquire in order to take on maybe these jobs that are currently hiring if I had been furloughed or laid off due to the ongoing pandemic. And so this was part of a global skilling event that was a joint announcement between Microsoft and LinkedIn. And if you notice, these queries are precisely top K queries, like what are the top employers, what are the top jobs, what are the top skills. So we could apply our algorithms on top of this. And we have, you can visit this site and explore the data to sort of see these various breakdowns to see like what are the most top trending employers. And like one thing that was interesting is like before February, you weren't even seeing DoorDash, and then all of a sudden DoorDash was coming up in the top 10 for top showing up in the results. And we have this sort of privacy blurb on the site that sort of explains that we're using differential privacy in these counts. One thing that I don't show is that we also show top skills, and we're only using the unknown Gumbel without adding noise to them. So we only are providing a ranked list because somebody might have multiple skills. So for more information, we have this archive paper describing what we did. One thing to point out is that even though this is sort of not like provide these insights quickly because these sort of being reported every month, it was still interesting to add sort of the unknown domain algorithms to it because we didn't want to show possibly jobs in these results that possibly nobody actually got hired during that previous, I think it's quarter. So if we have, if we're only enforcing sort of people have to be hired from a job, then we have to have positive counts so we can sort of apply through. So for more information, see the post. And another very interesting application, this is sort of the first one that we worked on, was something called the Audience Engagement API, which was providing these external marketing partners or think of advertisers, sort of insights on how LinkedIn members are engaging with various content and audience data. And it's built on top of this product Pinot that I was describing earlier for fast real-time data analytics. So it literally is like an API that advertisers can adjust their SQL query and get a result. And we need to privatize it. We need to fetch the result from Pinot and provide it back to the advertiser. Okay, so the task here is that an advertiser is going to be able to interact adaptively with the API. And this makes things like differencing attacks a real concern, like what are the top articles being viewed among all CEOs in the US, followed by what are the top articles being viewed among all CEOs in the US, except at LinkedIn. You can take a difference and identify what articles CEO of LinkedIn was looking at. And note that like thresholds or anything are not going to help you. So this brought up differential privacy. And so we wanted to be able to include it, but also respect the sort of real-time constraints for this application. And also the queries here are sort of these journal top K queries that sort of showing you queries that have a group by maybe some filters, like I want to know the top articles being viewed among all CEOs in the US CEOs at least 3 years, something like that, to provide these insights. Also, one thing to point out is that we want to be able to track and limit privacy budget for each partner. Like, it's not sufficient to just privatize each result, because an advertiser might ask lots of queries each one. So we want to be able to track and limit the privacy budget for each partner. Know that there's this assumption that sort of partners will not collude with each other. We don't want one partner being able to ask lots of queries and then block partners from accessing it. So currently it's only being shown to sort of trusted external partners that are not going to share their results. Another big thing that we needed to solve here was something like consistency, and the data was also being refreshed. While also some sort of old data is going to be dropped. So think of it as like each day I have a collection of new data that's going to be inserted in the data set. A larger data set that's more than 30 days old is going to be dropped. So there's no data from more than 30 days prior. But also know that the data set is sort of stagnant for a given day. So if anyone asks the same query on the same data, on the same date, sorry, that should be on the same date, we want to be able to provide the same. And so the way that we do this is with a random seed generation that was kind of the results of Kinthapati and Tran, where we want to ensure consistency by essentially using a pseudo-random seed in our algorithms that is going to be a hash of like a secure key, as well as concatenated with like the query and concatenated with the date. So if somebody asks the same query on the same date, we know we will give the same noise, and the data hasn't changed, so we would give the same result. So for more information on this, we have this paper that was actually recently accepted to JPC, which is interesting for a paper about advertising to be accepted to a privacy journal. Okay, so now I want to talk about some streaming algorithms. I should pause for here. Okay, so I'll move on to the stream.
I have a question, Ryan. Sorry, we were just unmuting. So can you explain what types of queries the API supports for these sort of audience analytics? Like, what,
yeah, so
you know, how rich a set of kind of how let me put it this way, like how close is the API to what advertisers would want in terms of access to who's watching and seeing ads and stuff?
Yeah, so the Pinot kind of has some restrictions on its own on like what SQL queries could, or you can't do like subqueries, which drastically reduces the number of things you can do. Kind of that structure that I showed earlier, this sort of SQL query that had a select, and you could do a count star or distinct count. You could do several where clauses, and you could do a group by, and you could limit the number of things that are returned. You couldn't do a join. You can't do a join on data sets. You can't do several subqueries. So sort of already Pinot has some limitations to be asked. And so that allowed us to sort of just do focus on top K, where we could only do some filter clauses.
Do you have a sense of like what types of queries kind of well supported there, as opposed to, you know, like, you know, how does this sort of change the way advertisers access, you know, what kind of information they actually wind up getting access to? Does it sort of end up doing everything they want, or does it sort of say, oh, well, you can only get information about large campaigns, or?
Yeah. So we've gotten some feedback on sort of like what they want, but kind of I don't know if there's been any complaints about sort of how rich the set of queries are that they're allowed to access. And I think it's also like they know that there's some privacy implemented. So sort of when they sort of add too many filters, like not getting any results means that like sort of the data is low volume. So yeah, I think the expectations are sort of set.
All right, thanks.
Yeah. So let me go on to sort of like what some sort of earlier work in this sort of streaming data model. And what I want to sort of contrast here is sort of like what I sort of finished off with the last application, using this timestamp to ensure consistency in each result. And so I'll call that the sort of data refresh model, where we have each day's events being thrown into the data sort of in a batch, and then some old events sort of being dropped each day. But each day the data set is fixed. So to ensure privacy, what we can do is we can just add fresh noise. So if they ask the same query in the same day, they get the same noise. Another thing is that the user's data is present for only a short amount of time. Maybe it's sort of with this sort of rolling window, maybe the data set is completely different 15 days later or 30 days later, depending. And I want to sort of contrast that with like the sort of data streaming model, where in real time and they're just being thrown into the data set and appended and getting larger and larger and larger. Maybe the data set is sort of stops at and maybe just gets completely wiped out in like maybe that, but the sort of time range is a lot longer. And so the point here is that for each query that's asked on this data, we can't sort of add a pseudo random seed that depends on the date, because the sort of new events are streaming in real time. Each day we might have a totally different data set at every millisecond. So fresh noise would have to be added after each event, and a user's data can be present. So with that, I want to motivate the continual observation model, sort of developed by Chan et al. And Dwork et al. About 10 years ago. Here the data is going to be streaming in real time, and whenever we issue a query, the data may or may not change. We just don't know. And we want to be able to we could still use our sort of differentially private algorithms that I talked about in this 2x2 grid, but we just can't use the date in the seed. So every time somebody asks the same a query, we just be adding fresh noise. And so I'll talk these algorithms that are going to be adding fresh noise every time is like one-shot algorithms, because we're going to be treating them as sort of independent, treated independently on a given data set at any time. So if I issue one query, I need to add fresh noise, ask the same query, I have to do fresh noise again. And so what is this going to do to the privacy law? Is it's going to sort of make it kind of go out of control. Like if I issue the same query multiple times and I sort of update it with every new event, privacy loss is going to be huge, or I'll just have to sort of stop access to it after a certain number of cases. And so the privacy loss is going to scale with the number of queries that are asked, or square root of the number of queries that are asked. In the continual observation setting, if we are going to be asking the same query repeatedly, we know that we can actually have privacy loss that scales like logarithmically or polylogarithmically with the number of queries that are asked. And so let me talk about this great primitive, the binary mechanism in this model. Consider the query that's like, give me a stream of people that have bought a particular drug from a pharmacy, and maybe every event is like a customer entering the pharmacy. So we want to, at each event, we sort of have a 0 customer bought drug A or not. And right above each event, I'm going to be showing the sort of streaming count. So after the first customer, they bought drug A, so the running count is 1. The second customer comes in, did not buy drug A. Now the running count is still 1. And continue the stream in exactly this way. So the third customer buys drug A, and so we increase the running count. Okay. So one way to sort of represent this stream or to privatize this stream is maybe in the local model, you would privatize every event. So like change the drug purchase A from a 1 to a 0 or a 0 to a 1. That will ensure privacy over the entire stream. We can release all the counts, but the noise will be terrible. We'll be adding a ton of noise. Or we could be doing exactly like sort of applying the one shot every round. But as I said, like the privacy loss will get too big, especially if this stream might be like millions of customers entering the pharmacy. Okay, so let's just represent this stream in a slightly different way, sort of with this binary partial sum table, where the second row of this table, I'm just going to take the sort of pairs of things above it and add them together to sort of make this partial sum. So on the second row, the first cell is going to be the sum of the 2 cells above it. The second cell is going to be the sum of the 2 cells above it, so on and so forth. And then the third row is exactly the same way. I sum the 2 cells directly above it, so on and so forth, until I get to the full sum of the stream. So now if I want the sum at any given time, maybe at round 7, I just sum up these bins, right? Which might seem crazy to do, but for privacy, it will make sense because if I were to think of sort of event level privacy, where I modify a single event, maybe I change the count of the 4th customer from purchasing drug A to not purchasing drug A, that will change only log number of cells in this table. So count at any one time, I only have to sort of go through the number of things that have changed in exactly one place. So the sensitivity of this whole table is only log of the full length of the stream, right? Because I can only modify the height of this binary sum tree. And so that means that the error that we're going to have to pay will be polylog of the stream size, because if we add sort of noise in every one of these cells, then we only, then the running count at any one time is going through at most log of these cells. Okay, so that's the binary mechanism. We then want to sort of extend this to not just a stream for a single counter, but maybe a stream over several counters. So maybe I'm not just interested in the purchases of drug A, but I want to know the purchases over all drugs. Like maybe a customer comes in and buys a bundle of drugs. So the first person's going to enter, buys drug A. The second customer comes in, buys drug B and C, so on and so forth. And I sort of want to provide a sort of running histogram over all of these drugs. So after 4 customers, I want to see sort of like, these are the numbers of drug A, this is the number of drug B, so on and so forth. And so what I can do is I can sort of form this partial sum table for all the drugs that can possibly be in this stream. But then several questions arise when you do this. Do we know all the drugs in advance in this stream, kind of like the unknown domain setting? And also, how many drugs can be purchased at one time? So typically in the continual observation setting, we're going to be mostly interested in like event level privacy. So changing a single one of these cells in the top row. But one event can contain lots of different items in it. So maybe we're talking about skills, like what are the top skills? one user can have lots of different skills. So you would have lots of items in every one of these cells. And so before we had these one-shot algorithms that sort of had this sort of top K or histogram algorithm to be in this 2x2 table. But now in the continual observation setting, it's kind of more open. Like we can certainly extend the binary mechanism to apply to lots of different counters, but we sort of need to know what the counters are. Like what are we providing counts for in advance? And so we have the known domain setting. And also it's in the L0 restricted sensitivity set. There's this assumption that each event can element, or maybe it contains multiple elements, but a user can only modify one of them. So kind of what was not maybe like a top K stream, right? If somebody can have lots of different drug purchases, maybe I only want to return the top three every round. Okay, so one thing is so the table can be easily filled out with sort of using a more meta of taking our one-shot algorithms to continual observation. You're going to basically put the one-shot algorithm in each one of these cells of your partial sum table, and to get the maybe top in each result for each running cell, you're just going to sort of aggregate all the cells to get sort of a histogram at every time. So the downside of this approach is that it's going to require applying the differentially private algorithm to various substreams. So if I have a full stream and I want to know what are what's the top drug purchase after 1,000 customers have entered the store, the sort of run a one-shot algorithm with sort of all these different substreams for that query. And it's just not feasible with existing infrastructure. We can't sort of slice and dice the stream and run algorithms on different parts of it to provide the count in any given round. But note that the binary mechanism can be implemented in a setting where we, at any one time, we only know the total number of it, and we know the sort of breakdown of the counts. So the binary mechanism, the way is we can just take the true count at one time and then do like a binary representation of the number of events that have occurred in the stream, and then we can sort of use a pseudo-random seed to determine which noise or which cells are added to give you the noisy count at any one time. So I now want to talk about sort of more practical of algorithms that can sort of fill out this 2x2 grid in the continual observation setting. So I'm running a little bit low on time, so maybe I'll only describe like one of the, or maybe two of these algorithms. So the main question where we know the domain, but a user can, or an event can contain lots of items, is essentially just asking, is there an exponential mechanism equivalent in the continual observation setting? Like we want to just release top one a certain number of times. And the sort of desired behavior here is that we would have something that would have error that sort of would grow only logarithmically with the stream size. And unfortunately, recent work from Jane et al. Show that for what they call the sum select problem, which is precisely the top one case, there's this unfortunate lower bound that essentially has these various terms, and I'll sort of point out that sort of this term has a matching upper bound by just applying the exponential mechanism at regular intervals. So you're just going to sort of release the, you're just going to find the top one, use that same one for a certain number of rounds, and then after a certain amount of time, you're going to rerun the exponential mechanism. the other term in this lower bound is essentially just using the binary mechanism. So you know all the domain elements, even though I'm returning top one, I'm still going to have to pay. You can modify. So you're just applying the binary mechanism. And so this kind of sucks, like you wish there was something better to do. But maybe if we assume some more structure on the data stream, something like what we call switches. So if the stream has at most like S is like the max element sort of changes at most S times, then we can get error that sort of the sort of rates that we would want sort of polylogarithmically with the stream size, but there's now this pesky number of switches parameter. And the algorithm is essentially like kind of what the lower bound has of running the exponential mechanism at different times, but you don't know when to actually rerun the exponential mechanism. So you're going to use sparse vector to determine when you should actually make these changes. And so the algorithm works by running an exponential mechanism, find the top one element, do on this selected element. So this will give you a running counter, and then you're going to go and fetch the max element in the stream of the thing that's not selected, and just check, is it ever my current streaming count? And for that, you can use the sparse vector to only pay for the number of times you actually switch. And so we have some plots, pretty noisy, but this is just on synthetic data. We have sort of a power law distribution, and we're just this. The sort of purple high curve there is just going to be applying the binary mechanism, but when you have a dimension of size 100, so it's adding quite a lot of noise, but eventually like it's getting the right max, and the max is sort of high enough. The brown curve, I think it's brown at the bottom, is essentially running this meta algorithm where you're just going to do exponential mechanism in every cell of this binary tree. And you're just going to aggregate to get the top one result. But as I said, like that's not very practical. So these other curves in between are sort of like tuning the parameters between like allowing more switches, or this eta parameters, like how significant, how much more than the does another max have to be in order for me to actually make a switch? So how much more above my max? Okay, so that's the sparse Gumbel algorithm. So now, what about in the unknown domain? Yeah.
Can I ask a question?
Yeah.
Yeah, I didn't quite understand what the bottom curve there was. Can you, it's a little hard to read the plot from over Zoom, but is that the meta known Gumbel? The one with the lowest error that looks like the sawtooth at the bottom of the graph?
Yeah. So, well, first off, like the sort of zigzag, any one time we could be adding lots of noise terms or a few noise terms, depending on the binary representation of it. But yeah, the bottom curve is take the binary tree and just apply in each one of these substreams, you're just going to be running exponential mechanism in that for that substream.
But then,
and then
how do you
to get
like,
so you're just going to combine them. You're just going, in each cell you have its top one element and you have its count. And you're just going to, if the count is missing when you make the aggregate, you assume it was 0 in that cell. And then you just sort of add them up.
But like, I'm confused because that sounds like, at least in the worst case, you could be getting like different counts for each period, like the counts of different things for each period. So how do you aggregate those?
Yeah. So it depends on the data distribution and what we're sampling from is sort of this power law or Zipf's law. And so like, we're not doing any switches in the data domain. We're just always sampling from this power law.
Your stream is IID. Is that, did I understand correctly? So you sort of expect there to be always the same thing in the lead.
Exactly. So in the beginning, like sort of with these other algorithms, like it might have selected the wrong max initially, and then it just sort of figure out that it picked the, then it switches, and then it's good.
Okay. All right. Thanks.
Yeah.
I just
Yeah, and so like when your paper came out, I was hoping that like, you know, the sort of meta algorithm could better accuracy, but unfortunately your lower bound says that that's not possible.
Right. I think Mariam wanted to point out that we're running a little low on time. So just so you know, we're sort of coming towards the end.
Yeah, so I'll just in this new AI stats paper that we have, we sort of fill the rest of this table. So the sort of sparse guide, like to make it for the unknown domain setting, replace the exponential mechanism with unknown gumball. And then for the unrestricted sensitivity setting, unfortunately, our algorithm is sort of like based on a stability-based histogram approach, where everything in our unknown domain setting, where we're only given like at every round the prime, but we actually have to have the full histogram. Some concluding remarks, because I think I'm out of time, is the privacy parameters in practice are turning out to be pretty large. And so we'd like to be able to rationalize these large parameters a little bit better. So it'd be great if there are sort of more open source sort of attacks that we could sort of motivate for why like privacy parameters might be able to level, or more pushback on, no, we can't go that large. Observation. For open research questions, lots of love to go over those maybe in the follow-up, but for people that need to leave, I'll any questions?
Thanks. Could you go back to that, leave us with that last slide to think about?
Yeah. Yeah, I can go over each one of these open problems that we have, if you like. It's kind of like, well, what if this sort of pre-processing top K algorithm, what if it's sort of doing an approximation of the top K? Like for distinct count, you know, there's like hyperlog log and some sketching algorithms. You know, I've frequently been told by people like, oh, don't worry, the top K prime solve. So there has to be some privacy guarantees. And yes, it has been shown that like some of these streaming algorithms themselves already ensure some level of privacy. Maybe you have to insert some additional data into it. But sort of some of the assumptions that we require in our algorithms of like actually getting the true top K sort of break down. And so we'd love to better understand like what happens with these approximation pre-processing steps.
Yeah, I guess it would be nice for those types of questions to be able to have like a kind of a crisp problem statement about what one might hope to achieve. And like, you know, is it like, are we looking for a particular level of utility for a particular class of streams or something like that, right?
Yeah, or like, you know, even like what should we use a totally different DP algorithm. Like for instance, like say that rather than getting the true distinct top or count distinct top K, we're getting like this hyperlog log version. What should the sort of algorithms that we apply to this histogram look like? Like what could we do to this as like a layer on top?
Okay,
So that's yeah, that's one question that we have. I can go through the others, but if I'd love to hear any questions or feedback from anyone else.
yes. Let's thank Ryan first, and then we'll open up the floor for questions.
Thanks.
Yeah, any question?
Maybe are there questions from people? If there are questions from people on Zoom, then
Maybe I'll stop sharing so I can actually see some people.
Well, yeah, not sure there's that much to see on Zoom, but maybe just coming back to the approximation question that you were just raising,
yeah.
Like, what is the, I was a little confused by the switch between counting distinct elements and heavy hitters. What, because you mentioned sort of, so there's two problems, and I think of them as different problems, but maybe there's sort of a connection that.
Yeah, so let me try to explain it like this. Like, if we do like a count query, we don't know the L infinity sensitivity in advance, right? We can sort of restrict the L0 sensitivity by sort of limiting the number of things we return or making an explicit assumption on how many things somebody can modify. But for the L infinity sensitivity, sort of the only way that we can sort of bound that is to change a count to a distinct count. That will ensure that sort of one person, if we remove them, can change a single bin by most one.
Oh, I see. So the issue is,
but now if we do a count query, runs very quickly. A distinct count query runs a lot slower. So the typical practice is to replace count distinct, the true count distinct, with a hyperlog log or something like that. Right. So now the algorithms that we have assume like, oh, we can bound the L infinity sensitivity by doing a count distinct. But to do that, we would want to input log. Now the assumptions that we had of like actually having the top K, the true top K, are no longer valid.
I see. All right. So like the counting distinct elements is happening sort of within each bin of the histogram, where you're asking,
exactly.
how many distinct people are there with this skill in this country?
Yep.
Right. And so the issue is, one issue there is just a sort of event, the privacy model as like event level versus, as opposed to kind of user level, like do you sort of, not so much event level versus user level, but like how many do you assume that a single person shows up only once in the stream?
Yeah, well, I think even more than that, like sort of an event here, like maybe an event is like clicking an article, right? And so maybe we don't need to do the restrict the L0 sensitivity, but an event here, like maybe I want to know like the top skills of people that have viewed article one person, when they view an article, that one event have lots of skills. So when we do a breakdown on skill, then the L0 sensitivity can be massive.
I see.
Even for event level privacy.
Right. All right, thank you. Any other questions?
So that's
So let's thank Ryan again. Ryan, you know, we definitely owe you lunch next time you're in Boston. So
Yeah.
you know, you're welcome to come sometime in person, give another talk maybe, or even if you're not giving a talk, we're happy to host you sometime.
Yeah, that'd be great. Yeah, love to come visit.
Okay, thanks again.
Yeah, thank you all.
Guys, in a couple of weeks.